This video, we're going to take a look at another example of our spring mass model, our vibration model, and let's see what we have. Mass weighing 8 pounds stretches a spring 2 feet, assuming that a damping force numerically equal to 2 times the instantaneous velocity acts on the system. Determine the general position of the mass as a function of t if an external force of f of t equals cosine of t pounds is applied for t greater than or equal to 0. Okay, so it's similar to a previous example that we've done with a few twists, but assuming you didn't watch that video, let's solve this in its entirety. So let's remind ourselves of our equation. So mx double dot plus beta x dot plus kx is equal to f of t. The first sentence here is going to allow us to solve for m, the mass of the object, and then k, the spring constant. So let's actually write that down. So we know that Hooke's law, the force needed to stretch or compress our spring, is going to be proportional to the displacement, how much we stretch or compress it. So in this case, our force is 8 pounds, and it stretches the spring 2 feet. So K is equal to 4, and then that would be pounds per foot, right? So pounds per foot. Let's see, it says that the weight of this object is given, so we know that weight is equal to mass times our gravitational constant. Taking the gravitational constant to be 32 feet per second squared, we get that weight of 8 is equal to our unknown mass, and then that's equal to 32. Can divide through by 32, and we'll get that m is 1/4, and our units here would be slugs, right? The beta is that damping force or frictional force, and it actually tells us that that force is numerically equal to 2 times the instantaneous velocity. So that's our beta. And then there's our external force. So there's a driving force here that's equal to cosine of t. And this basically is just saying that it's applied. You can't really see that for that on the white background, but that condition is basically saying that that force is applied from the initial time that the system is turned on, and it's left on forever. All right. So then let's write down the differential equation that we have. So we have 1/4 times x double dot plus 2x dot plus 4 times the x is equal to cosine of t. And this is a Nolde. This is a non-homogeneous equation. So we're going to have to solve this in 2 steps. We're going to have to find our x sub c and our x sub p. And we'll use our method of undetermined coefficients because this forcing function is simple enough, right? No need to complicate it with something like the variation of parameters. But I'm going to rewrite the equation so that we have nice integer coefficients. I'm going to multiply through by 4. So I have x double dot plus 8x dot plus 16x is equal to 4 cosine of t. So let's do our 2 steps. So 4, and actually let me scroll up a little bit more, get some more room. So 4 x sub c, or complementary function. If you recall, that's when we have to solve the corresponding homogeneous equation. Right, so assuming that there is no external force just for this instant, and then our auxiliary equation is m squared plus 8m plus 16 is equal to 0. And if you look closely, this is a perfect square. It factors to m plus 4. That quantity squared is equal to 0. So the roots are m1 and m2. That's our m, and that's -4. We have the repeated case. And just as a reminder, for the repeated case, the basis of all solutions is e to the -4t, and then t e to the -4t. So let's write down, so x sub c, which is our complementary position or displacement function, is c1 e to the -4t plus c2 t e to the -4t, right? Okay, so we have, I guess you could say half of it. Let's see how much work we will need to come up with the particular now, because what we want to do is we want to apply both superposition principles. The first one tells us that this linear combination here always satisfies the homogeneous case, and now we need to add our x sub p on. So this is where, using the method of undetermined coefficients, we look at our forcing function or function on the right and say, well, what would that x function have to be? Well, it would have to be a combination of sine and cosine. So let x sub p be equal to a cosine of t plus b sine of t. Right, so it has to be sinusoids, and they have to have the same period slash frequency for this to work. So in order to figure out a and b, we need to find the first and second derivatives of this, or x dot, xp dot, that's equal to negative a sine of t plus b cosine of t, and then xp double dot is equal to negative a cosine of t minus b sine of t, right? So then we're going to plug these terms into the left-hand side and set it, we want it to be identically equal to 4 cosine of t, and see what kind of equation or system of equation we come up with, right? So it says take the second derivative, so negative a cosine of t minus b sine of t, and then plus 8 times the first derivative, so that gives us minus 8a sine of t plus 8b cosine of t, and then plus 16 times the our original guess, plus 16a cosine of t plus 16b sine of t, and then that has to be identically equal to 4 cosine of t. Now, let's look at the like terms. Let's group these together. So let's group the cosine terms first. So we have a negative a, and then a plus 8b, and then a plus 16a. So that gives us 15a, and then plus 8b, that quantity times cosine. So we've grouped all the cosine terms. Let me cross out the ones that we just used. This one, and this one, right? So we're just looking at the coefficients, adding them, and simplifying as much as possible. Let's do the same for the sine now. So plus, and there's the quantity. So there's a negative 8a sine t. That's the only a coefficient for sine, so there's that one. But then we have two more for with a b. So we have a negative b plus a 16b, so that's plus 15b times the sine of t, and then that is identically 4 cosine of t. Now, since we want both these sides to be equivalent, then the coefficient of cosine on the left has to be equal to the coefficient of cosine on the right, and similarly, the coefficient of sine has to be equal to the coefficient of sine on the right. Well, we don't have a sine term here. That implies that the coefficient is 0, right? So here's our system. We're going to set that coefficient equal to 4, and then we're going to set that coefficient equal to 0, and let's see what we end up getting. So let me scroll down some more. So therefore, 15a plus 8b is equal to 4, and then negative 8a plus 15b is equal to 0. Now you could solve this using lots of fancy techniques. I'm just going to use a basic substitution. So I'm going to solve this equation for b. So I'm going to add the 8a to both sides and then divide by 15. So it's 15b is equal to 8a. That means b is 8/15 a. All right, then I'm going to plug this into the first equation, so I'll end up having 15a plus 64, 8 times 8, so 64 fifteenths times a is equal to 4. Now 15 over 1 is the same as 225 over 15. 225 plus 64, that gives us 289 over 15 times a, that's equal to 4. So then multiply both sides by 15, divide both sides by 289, and you get that a is 60 over 289. And then if this is if a is 60 over 289, plugging this here, multiplying by 8 over 15, so b is 8 over 15 times 60 over 289, so that gives us 32 over 289. So what we just figured out now is the a and b in our particular solution. So then let's write down two important facts. So then the particular function is 60 over 289 times the cosine of b plus 32 over 289 times the sine of t. And then we know our general position or displacement function is our x sub c of t plus x sub p of t. So add this function to this function, and then here's our final answer. So it is c1 e to the negative 4t plus c2t e to the negative 4t, and then plus 60 over 289 cosine of t plus 32 over 289 sine of t, and then this would be in feet, right? And because we don't have, and because the question just asked for the general position function or equation of motion, then we would stop here. We don't have the information. We have neither initial nor boundary conditions to allow us to solve for C1 and C2. So there you go, another example of our spring mass model. This is an example of a driven system where we have an external force, and you can see it produced a nullity, which we have methods of solution. All right, we'll see you in the next video.